In this video, we're going to look at the Born-Haber cycle in a little more detail. The Born-Haber cycle describes the process of turning elements into an ionic compound, or a salt. This is a formation reaction. A formation reaction is where you form 1 mole of a compound from its constituent elements in their native states. If you need more material on this, check out your book, Chapter 9, Section 7. The Born-Haber process was designed because it lets us define the lattice energy, which is very, very difficult to measure. The lattice energy is the energy released when the gas phase ions come together to form 1 mole of a salt. For more information on lattice energy, check your book, Chapter 4, Section 1. This cycle is based on Hess's law. Hess's law states that the delta H reaction for a process is if that process is the sum of 2 or more processes, is equal to the sum of the delta H reaction of the constituent processes. Basically, if we know the energy changes associated with a multi-step transformation, we can use them to calculate the energy change of the overall transformation. For more information on Hess's law, check out your book, Chapter 9, Section 6. So we have to ask ourselves, what are the constituent processes for salt formation? This is the Born-Haber cycle diagram for calcium fluoride, CaF2. The overall process will take solid calcium and gaseous fluorine and convert them to a solid salt. The first step of this process is to get the calcium into the gas phase. So you just sublimate it, delta H sub calcium. First energy cost we pay. We also need to break the bonds between the fluorine atoms so that they are individual atoms. This is the bond energy of fluorine. In this case, we're going to need 2 moles of fluorine because the formula of our product salt is CaF2. We have the calcium in the gas phase, but now we need to ionize it. Calcium will form 2+ ions because it's in the second column of the S block. Each of those electrons we have to remove is associated with its own ionization potential. We'll need to add up both for this energy cost. Now those 2 moles of electrons released by the mole of calcium will then be absorbed by the 2 moles of fluorine atoms we have to make 2 moles of fluoride ions. This is going to release 2 equivalents of the electron affinity of fluorine. Remember, electron affinities are negative because adding electrons to atoms is a favorable process. Electrons like being close to atoms. The last step, now that we have both of our ions, is they're going to come together into calcium fluoride, the salt. This is going to release quite a lot of energy. I need to draw your attention to 2 similar but contrasting energies on this diagram. The first is the delta HF. Delta HF is the heat of formation of the calcium fluoride. This is the energy associated with that formation reaction, because you can see we've started with elements in their native states and we've gone to the salt. The second one is the UCaF2. This is the energy released when the calcium and fluoride ions come together to form the salt. This is the lattice energy of the compound. The heat of formation, delta HF, can be readily measured with calorimetry experiments. The lattice energy, on the other hand, is very difficult to measure directly. The Born-Haber cycle was designed to let us calculate it. Let's see what that looks like. In step 1, we're going to sublime the calcium, which is going to cost us 168 kilojoules per mole. In step 2, we're going to break the FF bond of F2, and that's going to cost us 155 kilojoules per mole. In step 3, we ionize the calcium, so it's going to go from calcium to calcium 2+ plus 2 electrons. That's going to cost us 590 kilojoules per mole for the first electron, and 1145 for the second. Then we'll ionize the fluorine. F plus an electron will go to F minus. The electron affinity of fluorine is -328, and we're going to need to count that twice because we're going to make 2 moles of fluoride ions. In the last step, we'll form the calcium fluoride. The ions will come together to make the salt. and this is the lattice energy, the one we do not know. We can look up the heat of formation of calcium fluoride in any number of references, or we could do an experiment ourselves. Either way, it's minus 1228 kilojoules per mole. Let's design the equation we'll need to use according to Hess's law. Here's the heat of formation. That heat of formation is going to be the sum of all of these other sub-processes that occur. We know all of these except for the UCAF2, or the lattice energy. So let's plug in all of our numbers and crunch them down. We find that UCAF2, or the lattice energy of this salt, is minus 2630 kilojoules per mole. That's a very large release of energy, so CaF2 would therefore be expected to be a very stable and not particularly soluble salt. I hope this helps you for your homework, and I'll see you guys in class.